So 10.4 is about area and length in polar coordinates. Let's do some problems. Number 11. Sketch the curve and find the area that it encloses. So we have to make a sketch and area. So for sketch, let's first write what is R for various data. Theta is 0, R is 5, theta pi over 2, cos pi over 2 is 0. Theta pi, cos pi is -1. Cos 3 pi over 2 is 0. So the sketch should look like this is theta equals 0. So this point then becomes 1 comma pi. So how did I know I have to pick this curve? Because if you remember, so this given curve is similar to right, but instead of 1 you have 3 and you have 2 multiplying cos theta. So this serve as a template for this. So if you recall, 1 plus cos theta was like something like this. At this point, so this is the template to draw this curve. Now we have used just correct values of R. So instead of these values, this 3 and 2 change the R values, and which is why this is now shifted, because for pi R is 1. So this is the sketch part. Now we have to find area. So the formula for area is from some theta A to theta B. So you have to memorize this formula for area in polar. R will be given as a function of theta. Square it, multiply by half, and integrate as with theta variable in some given region. So these endpoints will depend upon the area of the region we are calculating. So here the region is this whole curve. So here the theta goes from 0 to 2 pi. Let's first square it. This antiderivative we know, this we know. Here we have to use Drake identity. So we have 2 from here, 4 over 2 plus 9, 11. And 4 over 2 is 2 times cos 2 theta, and 12 cos 2. The sine of 2 pi or 2 times 2 pi, 4 pi is 0, sine 0 is 0. Again, sine 2 pi is 0, sine 0 is 0. So these two terms will give us 0. So the answer becomes 2 will cancel out. 11 pi. So area is again positive. It's equal to 11 pi. And let's do more problems. was 70. Find the area of the region enclosed by one loop of the curve. One loop of the curve. In the previous problem, we calculated the area inside the whole curve, but now one loop. So the curve is four cos 3 theta. Now how to find out the endpoints? So if you recall, yes, but now we need to find these endpoints that correspond to one loop. So the one way to do it is to find the integral bounds. So one way is difference or instead of difference you can say, well, let me not call it difference. Two consecutive values of theta which r is 0. So this will serve, so we have to compute what theta's r is 0, and then any two consecutive values will serve as the bounds. Let's see what I mean by this. For one loop. So we are interested in one loop. R equal to 0 means so cos theta is 0 at pi over 2, 3 pi over 2, and so on. Right. Odd multiples of pi over 2. N pi plus pi over 6, where n is some integer 0, 1, 2, 3, so on. And it can be either plus 1 or minus 1, plus 2 or minus 2, that's fine. So if you look at the consecutive values, So n equals 0 corresponds to theta equals pi over 6. Or you can say n equals 1 corresponds to theta equals which is pi over 2. Or you can also take n equals -1. So the consecutive values for theta are either negative pi over 6 and pi over 6 or pi over 6 and pi over 2. So if you look at the sketch, this is the loop that gets traced out for pi over 6 and pi over 2. And this is the loop that gets traced out between pi over 6 and negative pi over 6. So this is pi over 6. So when you go from pi over 6 to pi over 2, this is the loop that gets traced out. And when you go from negative pi over 6 to pi over 6, this is the loop that gets traced out. So one loop can be either this or that. The area is same. So I can either take pi over 6 to pi over 2. This refers to this loop. Or I can also take my limits as minus pi over 6 to pi over 6. This will correspond to that loop, while this corresponds to this loop. Area is same for both. Let's calculate the area. So we have to use trig identity here. This 2 cancel 16, so we have 8. And this 2 can also cancel this. So note that when I substitute pi over 2 here, 6 pi over 2 is 3 pi. Sine 3 pi is 0. When I substitute pi over 6, 6 pi would be pi. Sine pi is 0. This term will give me 0. So my area becomes which is 4 pi over 3. So the area for each loop here is 4 pi over 3. The bounds only determine which loop we are considering, but the area stays the same. And you don't have to sketch the loop. So if you just compute the r equals 0 points, then take consecutive values of theta, which r is 0, like here. And again, n can be 0, plus minus 1, plus minus 2, plus minus 3. So if we take 0 and negative 1 n, we get this loop. If we take 0 and 1, we trace out this loop. Then don't forget to square trig identity. Let's do next problem. And this is very important, the one loop problems. (23) Find the area of the region that lies inside the first curve and outside the second curve. Inside the first curve and inside the second curve. The curves given to us are, so the first curve is r equals 4 sine theta, and second curve is r equals 2. Let's first try to sketch these two curves. So the first curve is This is also a circle. We can see it. Multiplying r to both sides, r becomes r square, and then you get an r here. Now changing to Cartesian form, r square is x square plus y square, 4y. Next, complete square. Now to complete square, so if you remember the identity, we have y square, and this is negative 2 times 2y. So it means if we add and subtract 4, this becomes y minus 2 square. So then the equation becomes so this is a circle with radius as 2 and center at 0, 2. So curve 1 is a circle of radius 2 with center 0, 2. And curve 2, this is just a circle with radius 2 and center as origin. This is also a circle. Let's sketch these two. Let's make it. So this is second curve, r equal to the first curve is and this is first curve. Center 0, 2, radius 2. Now we have to find the area that's inside the first curve, outside the second curve. Inside the first curve, but outside the second curve. So we are talking about this region. and the endpoints of this region are these. So now we have to determine what are these values. These will be the bounds of integration. So now let's do that points of intersection. We equate the two curves. So this means sine theta is half. Is pi over 6 plus pi minus pi over 6, which is 5 pi over 6. Then this angle is 5 pi over 6. And this one is pi over 6. And this region is bounded, that curve 1, from the area of curve 1, we subtract this curve 2, area enclosed in curve 2. So for the shaded region, area is half pi over 6 to 5 pi over 6. The first curve squared minus second squared. And this will not be the case every time. Only in this problem it is like in this manner. That from the first curve we subtract out this, the part of the second curve. That's why we have first before second. Equals half. First curve squared is 16 sine squared theta. And second curve squared is 4. You can factor out of 4. And here we use trig identity. Factor out 4, we are left with 4 sine squared theta, and instead of sine squared theta, we use trig identity. That's it. Cancel this. 2 minus 1 is 1, and this 2 times negative cos 2 deltas. And this 2 will cancel out. Minus this term sine And one more point here. From the symmetry of the curve, you can change the bound to pi over 2 if you and multiply this part by 2. So you can take the integration from 0 to pi over 2 and then multiply by 2. Because the symmetry is like that. So you can integrate up till here and then multiply by 2. So here we have times 4 pi by 6 minus this 2, this 2, and this. Sign will be negative here. Be positive. So the area is again positive. Negative root 3 over negative root 3 over 2 is negative root 3 times negative 2, positive 2. So what I was saying, the symmetry argument will be, this equation is same as 2 times 1 over 2 pi over 6 to pi over 2. Same thing. So instead of this antiderivative, you can have 2 times pi over 6 to pi over 2. That will also give you the same answer. because of the symmetry. Let's do one more problem. This is inside both curves. Area inside. The curves are r equals 3 sine theta. So the first curve is and the second curve is so both are circles. So if we proceed in the previous manner, first curve, then we complete the perfect square. This is y minus 3/2. So the circle of radius 3/2 and centered at similarly. Second curve is 3 cos theta. And you can write it in the same manner. So by symmetry, we already know the answer. You will have x minus 3/2 squared plus y squared equals this. So let's complete the perfect square. This is so just like this curve. This is also a circle, but with radius centered at 3/2, 0 and same radius. Now let's sketch them first. This is the first curve. This is the second curve. This is second curve. This is first curve. The first curve is centered on y-axis. So the region that is inside both curves is this region. So let's first find this point. Integral bound. Points of intersection. Equate both the curves. So this is pi over 4. Now how to set it up? If you note that this line at the center, divide this into two equal parts. So let me write this here. So this is this. Now what we do is we take area of this region when we go around this circle from 0 to pi over 4. We take this region which is lies in this circle and which is traced out when we go from 0 to pi over 4, and we multiply this by 2. So this is just 2 times this region. So this first curve is r equals 3 sine theta. So we only work with this curve, r equals 3 sine theta. handwritings. And multiply by 2. That will give us this whole region. So this is a tricky problem in this sense. Then area is 2 times 0 to pi over 4. So here we are not really working with second curve. We're only taking curve 1 because when we travel along curve 1 from 0 to pi over 4, we get this region. And then this enclosed region is just twice of that. Now same method, trigger entity. So this 2 comes from this identity. So sine 2 times pi over 4 is sine pi over 2 and sine 0 is 0. So we get 9 pi over 8 minus 9 over 4. Because sine pi over 2 is 1. So again, this is a tricky problem, so be careful with it. Let's do one last problem. Which is number 47. exact length of the polar curve. So you have to remember the formula for polar curve. For some theta A to theta B. So r squared plus dr by theta squared. So this is same as the previous r line, but here you have polar. So this is an easy problem. So the curve that is given to us is r equal theta square. Let's compute dr over the theta. Now just substitute it here. And theta values is 0 to 2 pi. So we have to find the exact length of this curve from theta 0 to 2 pi. R is theta squared, r squared would be theta 4. dr by dt is 2 theta. Squared will be 4 theta squared. You can factor out theta squared. And this is simple U substitution. So note, I'm not using any limits right now. If I have to use limits, I have to use the limits for U. Right. So then U is theta squared plus 4. So only after changing back to theta, I'm using the limits. So 4, square root of 4 is 2, 2 cube is 8. So that's your final. Because if you factor out a 4, it has 3 halves. So 4 3 halves is 8. So this is an easy problem, but you have to memorize the formula.